Thanks. Hi, everybody. Welcome to AHA 2019. I'm here with our Vevo Travel Award winner for Cardiovascular, Jana Grune. Thanks for
Hi.
joining us.
Yeah, thank you for the invitation. Yeah.
You're welcome. Glad you could make it to the conference.
Sure.
Could you tell us a bit about your research, what you're working on?
Yes, of course. So this research project was based on an accidental finding, basically.
Oh, those are fun.
Yeah, of course. Yeah. So this is why. So I wasn't aware that all of this will happen to me or to my research. So basically, the New Zealand obese mouse is a mouse model which is used in metabolic research as a diabetes or obesity model. And there was a group using this model before, and they reached out to me and asked me if I could screen these mice for cardiovascular damage events in a kind of time course here.
Okay.
And therefore, it was really surprising that these mice had a lot of aortic valve damage. And this causes the end organ damage of all the ventricles, so of the left ventricle, the lung, and also the right ventricle.
And it's primarily the aortic valve?
Exactly.
Okay.
Yeah.
So the tricuspid and the mitral and the pulmonic all seem to be fine or fine-ish?
It depends on the time period where you screen these mice, right?
Okay.
So because if the aortic valve is damaged, it won't take a long time to get the ventricles damaged.
Sure.
And the longer you let these mice sit, the more damage is done also to the other end organs, right?
Okay.
Yeah.
And everything just obviously feeds back down through the system.
Exactly.
Yeah. Okay. Do they have any other sort of interesting cardiovascular phenotypes initially? There's changes in flow patterns or in strain?
Yeah, right. So the damage of the aortic valve, which happens pretty early, so already in living week 6 till 8, this is what we think at the moment. And this leads to a functional aortic valve stenosis. So the velocity profiles of the aortic arch are highly increased.
Okay.
And this is also comparable with severe aortic valve stenosis from humans. So very translational.
Okay. So you get that pressure backloading effect. And
Exactly.
Then wall thickening, things like that.
And over time, this effect leads to aortic regurgitation. So the aortic valve is not closing anymore. And this is what is kind of last stage disease here. So if the aortic valve is not closing anymore, the ventricle isn't able to maintain its function anymore.
Sure. Okay. So you mentioned it was an accidental discovery. So the accidental part was just the cardiovascular effects in these mice. They didn't realize.
So in the beginning, we weren't aware if there are any cardiovascular events in these mice because these mice are known for diabetes and also for obesity.
Okay.
This was already described earlier, but they have never been screened for cardiovascular events.
Okay.
So we did a huge study with, I guess, 250 mice
wow.
here and did serial echoes and also other cardiovascular methods to screen for cardiovascular events. But this effect was very striking. And the interesting part is that this only happens to male New Zealand obese mice. So
really?
this phenotype wasn't present in the females.
Oh, interesting. So there's a sex chromosome linked effect of it or
Might
something,
be, yeah.
possibly.
But yeah, as you probably know, in cardiovascular research, it's always that.
Nice. Yeah.
I'm sorry to say.
Well, no, don't be sorry. It is kind of an odd
Yeah.
thing, and I feel like in the past few years that's something that people have started to point out, that especially with some of the drug testing, that hey, by the way, you're only using this on male mice or male rats. You're missing 50% of the population.
That's true. Yeah.
It's a bit strange. So interesting. So how did you? What kind of parts of the Vevo imaging system did you use then on the animals? Obviously, then sort of full cardiovascular exams. Modes.
So in the beginning, we just looked at the left ventricle with regular B and M mode imaging, of course. But when we figured out that there is a problem with the valves and also probably with the right ventricle at a later time point here, we also used some more imaging stuff over here. So for the velocity profiles, of course, we used the Doppler.
Sure.
And for the valve imaging itself, we changed the probe. So usually we are using the 400 probe.
Yep.
But because you need a really high resolution for this one with high frequency, we switched to the 700 probe, which is, I guess, usually intended for the vascular stuff, right?
Typically more superficial, more vascular, sort of neonate scanning. Yeah. So how big are the mice then typically?
Well, it depends. So the male New Zealand obese mouse is between 60 and 100 gram.
Oh wow.
So this is really a huge and really fat mouse.
That's impressive. And you were able to get really
Exactly.
Excellent reproducible images of the
Right.
aortic
So
valve?
you need to be very precise.
Sure.
Also, if you need to scan the valve, so you really need the correct angle. So it's not easy, but manageable.
Sure, that's amazing. That's amazing to take that, because I mean, that probe, that 700 probe is typically used in, say, neonate cardiology or superficial vascular research. So to be able to use it on something,
so
like
I wasn't
that,
really sure
fantastic.
if this is working, but it was. And what we did as a second approach here, because we in the 2D images of the aortic arch, we saw that these mice are suffering from aortic dilatation.
Okay.
And therefore, we used the 3D motor to get 3D images or cine loops of the aortic arch, and quantified the volume of the aortic arch, which we already saw in the 2D images, but it was a very nice to approve this with 3D echo, which is more precise, right? Yeah.
Definitely. Yeah. So it sounds like you were really building up a fairly large data set across a bunch of different modes in these animals.
Yeah.
Good. And a fairly large study. You mentioned the study cohort was several hundred mice.
So this was really hard in the beginning because we needed to look at so many different organs. So starting with the aortic valve and the velocity profiles, the left ventricle. Then we did some lung ultrasound, which is probably a very new technique in small animals.
In
the clinics, it's pretty good, standardized.
Yeah, we hear about that often in the clinic, sort of looking at the noise profiles in the lungs. So that was a similar approach?
So it's basically more like scanning artifacts, but if you know how to read these artifacts, it's easy to say from these images, this is now congestion or not.
Right.
So you can easily distinguish between healthy and diseased mice.
Any chance of publishing anything on that specifically, like a techniques paper or?
So there is one paper out already, and we do have a review article at the moment in revision. So this is a technique we want to use now on a standard basis in our lab, because this is the only technique which can quantify lung congestion in vivo and at a serial manner, right? So usually you need to sacrifice the mice and quantify the lung wet to dry ratio. And this is way more beneficial to do it every single week. Or
it is. Yeah, that's interesting. So I think a techniques paper on that would be really powerful. Not obviously just for cardio, but we have a fairly good number of researchers in cancer work that are looking at lung cancer models.
Yeah, right.
And there's always been a real challenge to try to use the ultrasound system to look at these lung tumor models.
So be sure we are working on this at the moment. So.
Fantastic, that's good.
But of course, you need a huge database to set up a kind of score or scoring system.
Sure.
So which pathology is really showing these artifacts or that artifacts. So this is what we are trying to figure out at the moment, because I guess it's not really helpful to have a score which works for all of the pathologies. You need to be more specific.
Right.
So probably the lung cancer people do need another score than we do in pulmonary hypertension or
to look for a different pattern.
Edema, exactly. Right. Yeah.
Cool. So we were really thrilled to see the paper come out that you did on the Auto LV tool, on the artificial intelligence tool. That was fantastic. What can you tell us about your experience working with that tool and with artificial intelligence in general?
Yeah. So basically, this was, this is the first tool on artificial intelligence and small animal echocardiography. And what we did over there, so we used our database from several different pathologies and animal models, and tried to screen if the automatic tool is working in the way like we do it in a manual way usually. And this was a lot of fun because if you already have the manual assessed data set, it's just a click with a button, and you can see if this new data set with the automated tool matches your manually assessed data, right? Yeah. So therefore, was easy to get this data. And what I learned from this, or which was very new to me, is that not all of the pathologies were able to be scanned with the automated tool.
Right.
As we already discussed yesterday. So in the beginning, I thought it's probably more like it's working or not. So 100% or 0%.
Right.
But it came up. So we came up with a kind of 80% result here because 5 out of 8 animal models we were able to scan these 2 with the automated tool.
Sure.
And the other ones, we do need a little bit more improvement here to also assess these with the automated tool. Right?
That's good, and that's fantastic. Like for us as a company on that product, that's fantastic feedback for us to have. We already suspected that there were some gaps in the capabilities. So seeing that, I mean, we've fortunately.
But it's the very first software release, so therefore, I guess nobody assumes that this is now the perfect solution for everybody.
Right.
So, but we need to work on this, and I guess we figure it out. Right?
Definitely, There's definitely opportunities that we have to be able to add new training sets to it and try to improve
That's great.
it. So, I mean, I can really see not only from this conference, but from some of the other cardiovascular conferences that I go to, that there's such a amount of interest and focus on artificial intelligence tools right now.
And especially for these huge projects where you have hundreds of mice or images or cine loops, you really need this automated tool, right? So because it takes forever to do the analysis.
Yeah, I mean, data analysis is always a big throughput. I remember when I was in grad school, and it was the same thing. It was like 80 or 90% of the time is data analysis. And 10 or 15% is data collection.
So getting the cine loops is just a tiny part of the work, right?
Then it's a lot of coffee and snacks in front of the computer, just analyzing and analyzing. Sure, good. So you were one of our travel award winners for the cardiovascular track. What can you tell us about how the cardiovascular award? Well, cardiovascular award is probably the wrong thing to say. The travel award. What can you tell us about how the travel award has helped you out to further your research?
Yeah, I guess without the travel award, I wouldn't be here probably because I need the money or use the money to come here.
Yes.
So even if I can't travel by train, you probably know that that's very expensive in the US, and therefore it always helps to be present at these kind of huge or large conferences. So this helps me a lot because I can talk to you guys, of course. Get in touch with other people. There were some people interested also in the research yesterday, the poster presentation. So it helps a lot, basically.
Great. Just provides some opportunities for interacting and disseminating science and discussing. Wonderful. Oh, great. So what's in the future for you in the next few years in terms of research?
Actually don't know. So as you may know, I moved to Boston half a year ago, and now I have new projects, of course, which are also based on cardiovascular research. And you never know which accidental finding you will make in these projects, right?
Yeah. Sort of the old joke where it's not a eureka moment. It's that's funny. That looks sort of odd. What is that? Great.
Yeah. So don't know.
Yeah. Okay. Well, great. We very glad that you were able to come and to meet up with us. And
thank you so much.
Thank you for taking the time to sit and talk with us. It's a pleasure meeting you.
Thank you.